All right, good afternoon, everybody. Welcome to lecture 26. This is part 2 of our discussion on horizon-based OpNav, and this will be the last of the content that you need to thrive on homework 6. And so I want to review, because it's been a minute. We haven't seen each other in a week. We had Monday off for the eclipse. So I'm going to share my screen, and we'll just go through our notes from OpNav part 1. So OpNav is our abbreviation for horizon-based optical navigation. And we started with this idea of, okay, here are 3 images. One is unresolved. Unresolved meaning that the thing you're taking a picture of looks like a dot. So you've got a dot of the moon and a dot of the Earth. And assuming you know which is which, and assuming you know where they are in space, like maybe you know what time it is, and you have spice ephemeris data, then this is enough information to navigate. You can kind of centroid the image to find the inertial bearing vector from the spacecraft to the moon, and then the spacecraft to the Earth, and then it's a triangulation problem from those 2 line of sight directions. So that's kind of one method of optical navigation or image-based navigation. Another is when the body has been resolved, and the body in this case would be like the moon or the Earth. So it's clearly a photo of the moon or the Earth, right? And in this situation, what you could do is find points that are on the edge or on the horizon, or what we call the lit limb of the planet. And it doesn't need to be the Earth or the moon. It could be Pluto. It could be, one of Saturn's moons, right? Anything like that. And then the idea being that you can fit an ellipse to that shape in the image. And then ultimately, based on the information on that ellipse, you can back out your relative position and attitude kind of question mark. So the attitude is a separate discussion, but we're going to focus on position in this class. And then the third example is when the surface features have been resolved. So you can clearly see not just the moon, but individual craters. Or let's say you were looking at an asteroid like Bennu, you can recognize individual rocks and you actually know their position in some global sense, right? There's some sort of shape model. In the case of the moon and on Mars, there are crater catalogs, which will tell you not where all the craters are, because it's, there's basically infinitely many craters, right? When you think about it, it's like a fractal pattern. But we could say all of the craters above a certain size, the same way that a star catalog couldn't possibly have all the stars, because there's basically infinitely many stars. But we could say all of the stars that are above a certain brightness, right? Then that's like, okay, well, that's actually something that we could try to do. And so correlating craters in the image to craters in a database ultimately gives you enough information to solve what's called the perspective endpoint problem. And that gives you your position and attitude relative to the moon or Mars or whatever else you want to work with. And so the horizon-based OpNav is the contents of homework 6. The surface relative, or in this case, terrain relative navigation is the topic of the optional homework 7 assignment. And so we're focusing on homework 6. And really what we're trying to do is put together a mathematical model that allows us to relate the relative position of the moon. I'm going to use the word moon by default, but it could be the Earth, it could be Pluto, take your pick. We're going to work through trying to come up with a mathematical model that relates the apparent limb points in the image. We'll talk about what limb means in this case, to the spacecraft position or the observer position, and ultimately use that to solve for our observer position. So we talked about the global shape of a celestial body, how we can come up with this matrix A, which is the planet shape matrix, if we treat it as a triaxial ellipsoid, and how A can be inverted, and it can be in the planet frame, or there's the principal frame. It could also be in the camera frame. We've kind of set up the problem of, okay, we've got some points on the surface of the moon, but those points are really, you could think of them as a rotation and a translation of a vector from the camera to an edge, a point on the edge of the moon. And we're kind of pushing in the direction of an equation which allows us to relate R, kind of the relative position of the two, to the observed horizon points. That's kind of what we're going for. And so we ended up with this idea of a quadric locus and a quadric. Actually, we didn't get to the quadric envelope. And I was just looking over my notes right before we started, and I think I'm going to leave off the quadric envelope. I don't think it's necessary. But we ended right here, and this was kind of our checkpoint, which is a point. This is the Greek letter zeta. Zeta is a vector from the spacecraft to a point on the edge of the moon. And there's some matrix QC, which has the planet shape matrix and the relative position of the planet and the spacecraft kind of baked into QC. So if we fully understood QC, we might be able to back out our position, right? That's kind of what we're thinking. And as a reminder, in this derivation, the hat symbol does not mean unit vector. It means homogeneous coordinates. So this is X, Y, Z, and then 1, right? And that's going to be necessary. I think, yep, so here's an example. The vector gets the regular kind of vector arrow, and then the hat means that we just append a 1 at the bottom of it, right? And that's going to be necessary. We use homogeneous coordinates to work with a rotation and a translation all in one matrix or homogeneous matrix. So that was the end of our discussion from last time. So why don't we get into the new content? And actually, I'm going to start with a quick aside to give you some terms, right? So first, quick aside. So if you're taking a picture of the moon, it's going to look like this, right? And then maybe it is a crescent moon. And then this part of the moon is dark because that's just the part that's not shaded, right? So you've got kind of the sun direction coming in from the right side. Then this side right here, I'm going to highlight in red. This area is called the limb. And then I'll change color to blue. This line right here I've somehow achieved erasing the line rather than drawing one. There we go. This line right here is called the terminator. The Terminator, obviously, is a robot that was sent back in time to kill Sarah Connor. But it's also the line between the light and dark part of the moon, or the Earth, or kind of take your pick, right? The difference between them is we use the limb to navigate. We do not use the Terminator to navigate, right? Because the Terminator is fuzzy. This is a fuzzy line. And the limb is going to be nice and sharp. Because the limb is the line between moon and space, but the terminator is the line between day and night. So you can imagine that the Earth, like where we are right now, the terminator is this line that is sweeping towards us at a rate of 15 degrees per hour. And when it hits us, it's sunset, and then it's nighttime, right? That's the idea. So the terminator is the day-night line, which is just spinning around the planet. But really, it's actually still, and the planet is what's doing the spinning, right? That's the idea. But when we're doing image processing, we focus on the limb. Now, if you've been blessed with an image that is just a full moon, then go for it. Just use the whole perimeter of the moon, right? But if you're working with a crescent image, then we are going to focus on limb points. So you might hear me use the phrase limb points when I mean horizon points. And so these would be limb points. And so ultimately, we're building in the direction of finding a series of these limb points, which all fit nicely to an ellipse. And now, even though we only have, 5, 6, 7, 8, however many limb points, it gives us enough information to back out the whole shape of the moon. I'm going to erase this in a second because I don't want that to be red. But so we don't use the terminator. I just want to be very clear when I use the word limb, the terminator, those are the two different lines I'm talking about. Okay. And so I'll make a point here. We focus on limb points. We focus limb points for OpNav image processing. Okay, so now back to our derivation, where we're ultimately building up into the direction of finding the position of the spacecraft with respect to the moon or the Earth, or take your pick. So the next concept is something called a celestial body's tightly bounding cone. So what does that mean? celestial bodies tightly bounding cone. Okay. So you can think of it this way. Every point in an image corresponds to a direction in 3D space. Okay, so the horizon points on a celestial body are image points, or I say correspond to image points, which are tangent to the body. So I'm going to draw a picture and hopefully this will make a lot of sense. And maybe this is even like an obvious statement, but if you've got your camera here and you've taken an image, right, and then you've got the actual moon out here, then your, here we go. Then all of the directions in the image, maybe I'll do 4 of them. 1, 2, 3, 4. That's good enough. Then the directions in the image, here we go. And maybe this is the lit limb that you can see. That's kind of the horizon that you can see in the image. There we go. There we go. So you've got 4 image points and then 4 corresponding points on the surface of the moon. And you can imagine these vectors kind of continuing off into space. What we've defined here is a tightly bounding cone. So it is a cone with a vertex at the observer's location. And then you can imagine that when you slice that cone, you're going to get a conic section, right? That's what a conic section means. When you slice the cone, you're going to get an ellipse, and that is going to be your image conic, or your image ellipse. So the visible ellipse in the image is really just what happens when you slice the cone at a certain location. And so the idea here being that information about the conic in the image can be used to back out information about the tightly bounding cone, which then, if you know the true size of the moon or Earth, or take your pick, that would then give you information about your distance and your relative pose. So I'll say this. Directions from the observer to the horizon form a tightly bounding cone and we're going to use the letter chi for tightly bounding cone. Looks like an X, but it's got like a little hook on the side. With an apex at a hat. Okay. And so you can think of it this way. Your tightly bounding cone is going to be proportional to QA transpose minus A transpose QA Q. Okay, where Q, just want to remind you, is the Q from the last lecture. So what is Q? We're going to go back one really quick. Q is this. This is kind of a combination of, we've got the planet shape matrix and the spacecraft position and the camera frame. kind of combinations of that allow us to build this Q matrix, which is really a quadric locus. You can think of it as the matrix for which all of these points are, any point on the surface of the moon, or any direction, I should say, from a spacecraft to the surface of the moon would have this equation be true. That's the idea. So Q is the 4x4 symmetric matrix describing this quadric locus in the camera frame. Well, Q is back again. And so the relationship between Q and the apex location gives us this information about chi, which is the tightly bounding cone. So let's add some more information here. So this is where chi is a 4x4 symmetric matrix of rank 3. And a direction zeta, hat, meaning its homogeneous coordinates, lies on the cone if zeta transpose chi zeta equals 0. So we said before that a point, the quadric locus gives us zeta transpose q zeta equals 0, but now we're saying zeta transpose chi zeta equals 0. So this is an even more, chi is even closer to what we're looking for, right? Because it was true for q. Q is points on the surface of the moon, but now we're talking about points or directions which form the tightly bounding cone. So we're slowly increasing the accuracy. We're getting closer and closer to what we're looking for. So let's start making this a little bit more real. If we have a camera and an ellipsoid in the camera frame, then, okay, so A is the vertex of the tightly bounding cone. And that would basically just be 0 in the camera frame, right? You're saying, well, no, I, the camera, am the vertex of the tightly bounding cone. But remember, it's homogeneous coordinates, so it's going to be a 4x1. So I'll clean this up here. So it's going to be 0, 0, 0, and then 1 is our A. Now, QC from last lecture is the planet shape matrix, negative planet shape matrix, spacecraft position, negative spacecraft position, transpose shape matrix, and then position, transpose shape matrix, position, -1. Right, that's Q from last lecture. So then we can do a fun bit of math. What is QC times A? Well, we'd basically just be keeping only the right side. So we'd end up with AC, RC, RC transpose, AC, RC -1. Okay, why did I bother multiplying QC by A? Well, because ultimately we need QC times A times QC times A transpose minus A QCA and then QC again. So we're going to kind of, here, one thing at a time. A transpose QCA would just be RC transpose AC RC -1. We're just keeping the bottom right component of the original QC matrix. And we have a little bit of other fun math to do. So chi is proportional to, okay, remember, it's QA transpose minus A transpose QAQ. So we have to go work that all out, right? It's going to be AC RC AC RC transpose minus AC RC RC transpose AC RC minus 1. And then we've got RC transpose AC RC minus 1 times negative AC RC transpose. Oh, sorry, that's transpose is on the outside of the parentheses. And then we've got RC transpose AC RC minus 1 quantity squared. This matrix is QC times A times QC times A transpose. Then we still need A transpose QA times Q. So we're still not done. This is minus RC transpose AC RC minus 1 being multiplied by the original Q matrix, which is AC, negative AC RC, negative RC transpose AC, RC transpose AC, RC minus 1. All right, so we've got some fun matrix math to do, and I'm going to skip a few steps because this is about to get really annoying if we don't. And I'll just say after simplifying, we get that chi is proportional to AC, RC, RC transpose AC minus, in parentheses, RC transpose AC, RC minus 1, close parentheses, times AC. All of that is a 3 by 3, and then it's zeros around the outside. So 0, 0, 0, 0, 0, 0, 0 creates a 4 by 4, which I'm just going to define this top left 3 by 3 as being something I'm going to call MC. And then 0, 0, 0, 0, 0, 0, 0. Good enough. And I guess because this is a definition, it gets the fun triangle, right? Now you might be thinking, okay, why am I saying that chi is proportional to this? Why am I not saying that chi is equal to this? Well, because the tightly bounding cone has an arbitrary scaling. So there's really no point trying to say what it's equal to. We're just going to say what it's proportional to. Similarly, imagine if you had a vector where the length of the vector didn't really matter. Well, then all you could really do is say what the vector is proportional to, right? Well, we know it's in that direction, but we don't know its length. So the chi vector or the chi matrix has arbitrary scaling, which we will eventually deal with. But for now, we're going to say that chi is this matrix, and we're further going to say that a direction, so you could think of these as limb points in the image, a direction lies on the tightly bounding cone if this is true. So if you start with those limb points, we might be able to back out some information about chi. That's kind of the idea. All right, so we almost have all of the tools that we need to proceed with solving the OpNav problem. All right, there's one more step. But let's pause here. Any questions on what we just learned? Doing all right so far?
Can you just scroll up a little bit?
Yes. Here, how much is a little bit? Is that enough for now?
Yeah, that, oh, wait, yeah, there.
Sure. Pause there for a second. So just to briefly summarize, the point of what we're trying to do here is we're building a matrix which contains information about the tightly bounding cone. And that tightly bounding cone, if you also know the planet shape matrix, gives you information about your position. So we're building in the direction of being able to solve for the spacecraft position R. And for those of you that know how to solve a Rubik's Cube, what's about to happen is things are going to get weirder and weirder and weirder, and then they're all going to fall into place right at the end. So you just got to keep bearing with me for a little bit. All right, am I good to proceed?
Yeah.
Awesome. All right, parameterization of a conic in an image. We haven't really spent that much time talking about the image processing side of things yet. We've just been saying, well, you've got some limb points. Let's talk a little bit more about the image parameterization. So in general, a generic conic section is given by, this is just true in general, A x squared plus bxy plus cy squared plus dx plus fy plus g equals 0, right? That's a generic conic section in two-dimensional space. And we have an ellipse whenever b squared minus 4ac, which sounds a little bit familiar from high school math, whenever that is a negative number, we've got an ellipse. And we have a circle whenever a minus c squared plus b squared equals 0. Now, in general, we're not going to have a circle in our image. Even if you're taking a picture of a sphere, that sphere, if you look at it from a glancing angle or, depending on your viewing geometry, could project into the image, giving you an ellipse, right? Unless you're looking directly at it. So we want to maintain a kind of a generality here. We're not going to jump to, well, it'll be a circle in the image. Like, no, you don't, there's no promise that it's going to be a circle in the image. So then, let's say, and this is still in 2D space for now, in homogeneous coordinates, x transpose, because I want to write it on its side for now, is going to be some x coordinate, some y coordinate, and then 1, right? Which might look a little bit familiar from our discussion on image processing and getting points in the image plane. So this is a point in the image plane, and we can say that x transpose cx is equal to 0, where c, and you know what, maybe what I'll do is it's fine for now. We're going to get away with this. C is a matrix, going to be a 3x3 matrix built out of A, B over 2, D over 2, B over 2 again. It's going to be symmetric. C, F over 2, D over 2, F over 2, and G. And this is where the matrix C contains the scalar C. So we're just going to say, don't get confused. That'll be the end of that. So C is one of the 6 parameters which describes a conic section or an ellipse in the image. But then we've got the matrix C, which describes all of them stacked together. So this matrix C is analogous to that matrix A we saw before, where A was the planet shape matrix. Well, this is the image conic matrix. Right? Just don't get those confused. Nice and simple. All right. What could possibly be confusing about using the same letters over and over again? C is a full rank, symmetric, 3x3 matrix describing the conic in the image plane. Put simply, C, the matrix C, describes the moon, Earth, Pluto, etc. in your image. Okay. We can compute the cone formed by backpropagation of an image conic. Because remember, we don't have access to the tightly bounding cone. All we have access to is points in the image which look like they're on the edge of the moon. So we're trying to keep moving in that direction. Okay, so I'm going to say then that P from A to B is a translation from A to B, and sorry, a rotation from A to B, and a translation. So this would be the position of B with respect to A. You could think of it that way. In much the same way, P from C to C would be the identity matrix and then just 3 zeros. So this would be a 3x4. Okay, keep bearing with me. This seems like a curveball. It's going to make sense in a second. The cone, the tightly bounding cone, is chi, which is proportional to P from C to C, C, P from C to C. Okay, so what this is saying is that the matrix C with 4 zeros on the right and 3 zeros on the bottom is proportional to the matrix where we've got MC and then the same configuration of zeros. Or the 3x3 matrix C, which describes our image conic, is proportional to the 3x3 matrix MC, which describes the tightly bounding cone. Okay, so let's put that even more clearly here. C is proportional to MC, and they're both proportional to, or I guess MC is equal to, I should say, equal to AC, RC, RC transpose, AC minus RC transpose, AC, RC minus 1 times AC. Okay, so this is an important checkpoint here. We're going to pause because this is getting a little squirrely. The conic of the planet, moon, etc., in the image plane is mathematically equivalent to a scaled form of the tightly bounding cone. So you could think of this as the tightly bounding cone, and this is the image conic. All right. This seems like common sense. Like if we go back up to our diagram for a second here, it seems to me like if we understood the image conic, we would understand the tightly bounding cone. But now we actually have mathematical proof that if you know one, you know the other. They are essentially the same information expressed in different ways. So I'm going to pause here for a second. Okay, so we are then very close to setting up the OpNav. As a matter of fact, I think we're basically there. I think it's time to set up and try to solve the OpNav problem then. So good pausing point. Questions on that? We're feeling all right so far. All right, so far so good. So then we will focus on horizon-based position estimation. All right. So we know, what do we know? An image conic obeys the constraint, that X transpose CX is equal to 0. And we know that C is proportional to this MC, which is our tightly bounding cone information. So if we put that together, we arrive at this equation, which was the equation we've kind of been foretelling for a while now, which is a point in the image plane which we know to be on the lit limb of the moon, Earth, etc., being multiplied by all this stuff. So AC, RC, RC transpose, AC minus RC transpose, AC, RC minus 1, AC times the point again is equal to 0. This equation is so important that I'm going to call it the asterisk equation because we're going to refer to back to it in the future. This is what we've been talking about for like 2 lectures now, almost, is, okay, we've got one equation which relates points in the image, which we know to be on the lit limb, to the planet shape matrix and the position of the spacecraft, which is fantastic. So now we just need to solve this problem, right? So I'll make a point here. We finally have our observations and our state in the same equation. So as navigators, we know that the battle is more than halfway won at that point. So the goal is to solve for RC, which is the position in the camera frame. Okay. Now, what's a trick that we can use? Well, here is something that can make our jobs a little bit easier. Since AC is symmetric, it can be factored as AC is equal to B transpose B, where B is some other matrix. Okay, so we're going to make sense out of B in a little bit, but we'll start with this. If AC was B transpose B, then our equation with the asterisk would look like X transpose, and let's see, this would be B transpose B RC, and then this would be RC transpose B transpose B minus RC transpose B transpose B RC minus 1 times B transpose B, X is equal to 0. Okay, and we can actually factor this even a little bit further. This is really saying that X transpose B transpose, and then we've got BRC transpose minus BRC transpose BRC minus 1 times the identity matrix BX is equal to 0. All we're doing is playing around with matrix math. Now, we still don't fully understand what B is. We're going to find that out in a minute. But we can see that this is starting to take this new shape, which I think is kind of neat. So we will define, we want to make our equation as simple as possible. X hat prime is BX hat. And similarly, RC prime is BRC. And forgive me for a second, I just found a mistake in my notes, so I want to clean that up. There we go. And if we do this, it's going to clean things up even further. Our equation now looks like X hat prime, so it's just scaled by some matrix B, which we don't understand yet, but that's okay. And then we've got RC prime transpose minus, in parentheses, RC prime transpose RC prime minus 1 times the identity matrix, X hat prime equal to 0. Okay. Might seem like we're further away from solving this problem, but actually we've gotten a little bit closer. So what we've really done here, is we've reached a point where we've described, so this describes the problem of navigating relative to a unit sphere. What the heck does that mean? We'll just say this. Imagine if the planet shape matrix was the identity matrix in the star equation that we saw before. So we'll go up for a second. The planet shape matrix is what contains information about the shape of the planet, as the name would imply. If we plugged in that AC was equal to identity in the star equation, we would be here, right? The difference is that we've done this by factorizing by this B matrix. So we've done some factorization to make the problem look like we're navigating relative to a unit sphere. So you can imagine, oh, I'm not floating over the moon. I'm now sitting in a Cartesian coordinate system looking down at a sphere with a radius of 1, and I'm navigating relative to that. And then later we can scale the problem back up. into the full 3D space, with all of our orbital mechanics going on. Okay. So now let's try to better understand that matrix B. Okay. So continue to bear with me here. Recall that AC is B transpose B. So all we've done is factorize the planet shape matrix. But we also know that AC is the attitude transformation matrix from the principal frame to the camera frame. And then we've got the shape matrix in the principal frame. And then this is TCP. And we also remember from last lecture that the attitude, so this is the planet shape matrix in its own principal reference frame is 1 over A squared, 1 over B squared, 1 over C squared, and that's a diagonal matrix. Okay. So we can leverage that actually. So we can just as easily say, that the planet shape matrix in the principal frame is really D transpose D, where D is equal to 1 over A, 1 over B, 1 over C. And then that would be a diagonal matrix as well. Right? If we do this, then we can say that AC is TP to C D transpose D T C to P, where this is going to be B transpose and this is going to be B. So therefore, B, matrix that we described a second ago, which allows us to do this factorization that we're so crazy about, is really D, which is just a modified form of the planet shape matrix, times T C to P, which gives you the attitude, the relative attitude of the camera and the planet frame, right? Okay. This is going to be very important as well. So this is the factorization matrix, which allows us to turn our problem of navigating relative to the moon into a problem of navigating relative to a unit sphere. So all of our work has gotten us to the point where we're now trying to solve this equation right here, this fellow. That's now what we're trying to solve. Okay. Just solving that is another full page of math, 2 pages of math. But then we're done. So we're getting there. We're almost there. Keep bearing with me. But does this jive? Does it make sense? We've made it to this point. Any questions on navigating relative to a unit sphere? All right. So let's talk about, we've set up the problem. Now we're solving the problem. Solving the problem of navigating with respect to a unit sphere. All right, this is a long section title here. Right. So let's say that we've got something like this going on. Here is the unit sphere. Here is a spacecraft. And so you can imagine that we're building a triangle from the center of the sphere to the spacecraft to a point on the horizon, which looks like this. So all of our fancy math has ultimately gotten us back to what looks like an SAT math problem. We know that this distance is 1 because it's a unit sphere, right? So the radius has to be 1. Okay. We are going to define this angle as being phi prime. We know that this vector on the top is x hat prime, and we're going to put the I on there. So it's the ith point, x hat prime. So this is a point in the image plane describing a limb point on the surface of the moon. It's in homogeneous coordinates, and it's been factored by this matrix B so that we know we're working relative to a unit sphere. And then this vector is the vector from the spacecraft to the planet, also factorized. So we've got This R is, I might even color code here. This R, which appears here, 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 and here, is this R. And then I'll switch to blue. This X is this X. So we've just drawn a picture describing this mathematical relationship here. Now, if we do a little bit of trig, remember SOHCAHTOA, we can say that the sine of phi prime is 1 over the norm of r prime. So sine is opposite over hypotenuse, right? That checks out. Similarly, the cosine, which is adjacent over hypotenuse, would be xi hat prime transpose r prime, and then normalized, right? So this would be divided by the norm of each. There we go. Now, what we're going to do to simplify our mathematics is we're going to introduce a new character. So we're going to define SI vector prime, and that's defined as XI prime normalized. Okay, so this is our image plane coordinate, okay? And that is now normalized. So what we're getting is a unit vector in 3D space. So this SI is going to be a unit vector in space. Now, how does that help us? It's going to make the equations just a little bit cleaner here. So keep bearing with me. So let's revisit this cosine equation then. If we do, then the cosine of phi prime is equal to SI prime, and then I'm just going to put this in parentheses, transpose, because it's going to get kind of complicated in a second. All we're doing is we're saying, well, look, isn't everything over here just SI prime transpose? Kind of what we're going for here, right? So this is this, and then on the right, we've got R prime normalized. Okay. Now, we're going to clean this up a little bit further. If we rework this equation, we get 1 is equal to SI prime transpose. And then on the right, we've got our position, and it's going to be our normalized position. You'll have to forgive me, my OneNote is lagging behind me for a little bit here. If this becomes an issue, I can just restart the thing. But we'll have a position, which is normalized, and then also we're going to have cosine of theta in the denominator. So it's going to be here divided by here, cosine of our angle phi. Okay, so far that's just some algebra. Now, what I'm going to do is even further simplify this and say that this is defined as being equal to the vector n. So our equation then looks like just the number 1 is equal to SI prime transpose n. Okay, where what? So n is some intermediate vector that we need. But we can see it's built out of your relative position and the angle between the line of sight to the center of the moon and the line of sight to the perimeter or the limb point. So it's built out of things that we understand. And then SI is the factorized, normalized line of sight direction in 3D space. So partially because I think that's already a natural pausing point, but also partially because my OneNote is giving me some problems. I think we're going to pause here. Yes, okay. It's a little bit, actually, I probably should have paused a little while ago. Sorry for dragging us on through this lecture for so long here. I'm excited because we're close to being done with OpNav, and it's going to be really cool when we see this all come together. It's about 7 now. Let's just say we'll take a break and we'll come back at 7:05. All right, I think we'll keep on moving here. Let's see. So as a reminder, here we go. Go into draw mode here. So we're back and we are kind of waist deep in this process of navigating with respect to a unit sphere. And we've arrived at this equation. And it's worth kind of pausing to think about what this means. So the line of sight direction from the spacecraft to a limb point, which has been like a factorized normalized direction, but ultimately it's a direction, and some intermediate vector n that we'd like to solve for. Okay, we can solve this problem. So let's assume that n is the key to our problem, which it kind of is. N contains information about our position as well as other stuff, but we would like n. The thing is that we have S. There's going to be several of them, right? And this is SI, so this is the ith point. So there's going to be several horizon points, which we ultimately factorize and normalize. And then we know it's true that for each of those points, this equation is satisfied. So what that means is if we have many horizon points, we can stack them to create a vector or matrix equation. So if we have many horizon points, we can solve for n using what else? Least squares. We understand that very well. So let's say we built a matrix which looks like this. S1 prime transpose all the way down to SM prime transpose. So what's this going to be? It's going to be a M by 3. It's going to be 3 wide and then M long. That's going to multiply some vector n, which is a 3 by 1, to get an array of 1s, which is ultimately going to be M by 1. Okay? And so we know that we can solve this problem for n. Okay, great. Now we have n, and it's not ni, it's not the n corresponding to the ith point, it's just n. Okay. We now know the normalized position and then also divided by the cosine of the angle. So how does that help us? Okay, well, let's go back to our equations. So now that we have n, our mission is to recover r prime. Okay, so as a reminder, the sine of phi prime is 1 over the norm of r prime. Okay, and we also know that n quantity norm squared, which is the same as n transpose n, well, that's 1 over the cosine squared of phi prime. And we can just kind of think about that for a second, right? N is going to be normalized r divided by the cosine of phi prime. If you do n transpose n and then work it out, the r's go away and you've just got the cosine of phi prime essentially. Now we know from trigonometry that the sine squared of any angle plus the cosine squared of that same angle has to be equal to 1. Okay? What that means is that the cosine of phi prime is 1 minus the sine squared of phi prime. Or, if we do some substitution, n transpose n, right? N transpose n is 1 over the cosine squared of phi prime. But then this would be equal to 1 over 1 minus 1 over the norm of r prime squared. That's a bit messy. You're doing a couple of different substitutions at the same time. But what we did is we substituted in, okay, 1 minus the sine squared of phi. So the sine of phi is this fellow, cosine is this fellow. If we do some kind of simplification, what we get is that n transpose n is the norm of r prime squared divided by the norm of r prime squared minus 1. All right. Now, if we work this around, what we can arrive at is, okay, n transpose n quantity times r prime squared minus 1 is equal to r prime norm squared. Okay. We distribute this, n transpose n norm of r prime squared minus n transpose n is equal to, oh no, OneNote's giving me a problem again. It could be a sign that even my software doesn't want to continue with this derivation, but we're so close. I realize that this is like the phase in solving the Rubik's Cube where things look like it's going off the rails, but actually we are a single digit number of lines of math away from being done with OpNav. So we're basically there. But it's always darkest before the dawn. It's OneNote. Oh, OneNote's crashing completely. Okay, love it. Here, bear with me for a second. I'm going to stop sharing and try to work the problem here. Hmm.
All right, so Paul has informed me that his computer is bricked, and he's going to try to reconvene at 7:30.
Thanks for letting us know.
No worries. Sorry about this from him. And from me too, I guess. While we're all sitting here, anybody get any cool Eclipse pics?
I didn't. It was cloudy, but one of my friends did in Vermont.
I got some good ones in Plattsburgh, New York, of like the total eclipse.
Yeah, I went home to like Watertown, New York, which is like I don't know 2.5 hours west of there, and it was all cloudy.
Dang.
I feel that. I was out at Rochester. We got cloud over as well.
Yeah, like it still got dark and everything, obviously, but just cloudy.
Oh yeah, still neat. Just no fun pics of it. More of an
Yeah.
experience, I guess.
Yeah.
Hey, I think I'm back. I'm still alive. Okay. Yeah, sorry about that, everybody. Are we still okay? Good. Oh, so the recording's gonna have about 20 minutes of dead air time now, but that's, I guess it could be worse. I hope everybody got the chance to take a breather during that period. Yeah, my computer just completely turned into a brick right in the middle of lecture. Like it not only did OneNote stop working, but WebEx stopped working. Everything stopped working at the same time. And you might think, oh, Paul's been gone for 20 minutes. He must have, taken a break and gone and gotten a bite to eat, maybe gone to the bathroom, and now he's back. It's like, no, no, I just restarted my computer. It took the full 20 minutes that I was gone to do that. This computer is definitely, I would say, circling the drain is probably still a compliment for where it actually is. So it's in rough shape. Um, so I hope folks are still here and these aren't just like a bunch of names that I see. Like I hope people are around. You've taken a bit of a break. So just to kind of recap where we were, so we were in the process of solving the problem of navigating with respect to a unit sphere. As we speak, I'm restarting OneNote and it's taking a second, so I'm just kind of padding for time. But I think it's good to recap because this is long after 7:30, and this is not supposed to be a long lecture, but we don't have very much math left to go, so we're just going to keep pushing and get this all finished up. So we spent all of last lecture and half of this lecture ultimately leading up to that equation, which I called equation star, equation asterisk, where we've got image plane points being multiplied by some stuff, which is ultimately this kind of twisted mess of position and planet shape matrix, which formed the tightly bounding cone. And so we had our measurements and our state in the same equation, which was great. We found that by factorization, we could reconsider the equation as if the planet or moon or whatever it was that we were navigating with respect to was a unit sphere rather than some more complicated shape. And then we spent the second half of the lecture solving the problem of navigating with respect to a unit sphere. We saw that we could use factorized, normalized line of sight coordinates to solve a least squares problem to get this vector n, as in November. And then we were in the middle of saying, okay, well, why do we care about that? Like, what is n bias? And the answer is that n can be used to back out our position, which is like what we're after. That's the whole point. So I'm going to go on sharing my screen, and we're all going to cross our fingers or say a little prayer that everything works. And yeah, if this became a recurring theme of like Paul's computer just completely shutting down, I would consider changing computers. But we've only got this lecture and next lecture, so kind of hoping that things will continue to work. So as soon as I'm successfully sharing, we'll wrap up. Because I believe we were in the process of reworking an equation that was a function of r and n. Yes, there we are. So just to recap, we've got the norm of the vector n squared is 1 over the cosine squared of this angle phi prime. What is phi prime? Phi prime is the angle between the vector from the spacecraft to the center of the moon and the vector from the spacecraft to a point on the surface of the moon. So this phi is directly related to how far away we are, right? And so the cosine squared of phi is related to n, the sine squared of phi is related to r. If we use this trig identity, we arrive at this equation, and I believe this is as far as we made it before. So we're going to continue now. And if we are to multiply this out, we get n transpose n times the norm of r prime squared minus n transpose n is equal to the norm, oops, that's meant to be r, not n, of r prime squared. Okay. And if we rework this, what we get is n transpose n minus 1 times the norm of r prime squared is equal to the norm of r prime. I'm sorry. I have this other way around. I done skipped a step. I was trying to do some fancy footwork here. This equation is true, but actually it is other way around. There we go. I tried to skip a step, do some fancy footwork here. There we are. And what this tells us is that we can rewrite the equation. The norm of r squared is n transpose n over n transpose n minus 1. Or the norm of r, which you could think of as the distance from the spacecraft to the moon, in this case it's with respect to a unit sphere, is just the square root of n transpose n over n transpose n minus 1. Okay, now we're still not quite done because we're trying to rebuild r, not the norm of r, but we've made a tremendous amount of progress, right? So we originally defined n as being what? Well, it's the vector r prime divided by the norm of r prime cosine of phi prime. Okay. Now, first of all, what we can tell from this is that this is just a scaling. Dividing by the cosine of phi prime is some scaling. Normalizing is just a scaling. This means that the vector n and the vector r prime are in the same direction. They're just scaled differently. Okay. If that's true, then n divided by the norm of n is equal to r prime divided by the norm of r prime. Okay. Or we could say r prime is n multiplied by the norm of r prime divided by the norm of n. Okay. But we know that the norm of r prime is all this stuff. That's why we bothered doing that. So we get that r prime is equal to square root of n transpose n divided by n transpose n minus 1 times 1 over the square root of n transpose n. This is dividing by the norm of n, right? And then this is multiplied by the vector n. Okay. And if we clean this up a little bit, right, we can, the numerator of this term and the denominator of this term cancel out. What we end up with is that r prime is n divided by square root of n transpose n minus 1. Now, just like solving a Rubik's Cube, where you might be thinking, wow, we are so many abstractions deep, I'm completely lost. It's like, no, you're not lost because we're done. 2 more turns of the cube and the whole problem is solved. Okay. So recall that RC, so we dropped the C subscript. This is the position in the camera frame prime. Well, that's just B or C. So the R, which is this R, is a scaled form of the actual position of the spacecraft. Therefore, we can say that the position of the spacecraft is B inverse times this, right? Or we could think of it this way. RC. So this is the actual position of the spacecraft in the camera frame. I should be very clear. This is the vector from the spacecraft to the planet, so it's the negative of the position. That's easy to get confused. Is B inverse n divided by n transpose n minus 1 square root. All right. But then we also know that B is really d TCP. So TCP, the attitude transformation matrix from the camera frame to the principal axis frame, and then D is a modified form of the planet shape matrix. Then we know that B inverse is DTCP inverse, which is the same thing as TP to C D inverse. where TP to C is known, or we assume that it's known. We're going to kind of brush past that for now. And then D inverse is just A, B, C along a diagonal, where those are the three primary axes of the ellipsoid that describes the planet that we're working with. So if we put everything together, we get this equation. The vector from the spacecraft to the planet in the camera frame is n transpose n minus 1 to the negative 1/2 power t p to c d inverse n. And that is it. We are done. This is the horizon-based OpNav equation, non-iterative. So this is the vector from spacecraft to planet in the camera frame. If you want it in some other frame, you'll need to do a rotation. If you want it to be from the planet to the spacecraft, you just take the negative, right? But this is the horizon-based OpNav equation, so it gets a big star. And I feel like we've now been wandering through this jungle of mathematics for long enough that it would be worth kind of reviewing everything that we just learned. So I'm going to do a quick kind of checklist. This is the checklist that you're going to do when the time comes to do homework 6. And then we can dismiss anybody, unless you have any questions, of course. I'll stick around afterwards. But this is our horizon-based OpNav procedure. Okay, so given, how do we want to set this up? I'm going to say given xi, and this is from I equals 1 to m. So this is given m, as in Mike, horizon points in the image plane. We're also assuming that we know the attitude transformation matrix from the camera frame to the principal axis frame. That is to say, we are not solving for, we're assuming we know the relative attitude of the planet and the spacecraft. And then we also assume that we know A, B, and C, which is the planet shape parameters. Right? So this is, in plain English, this is horizon points in the image plane, the camera attitude, and the planet shape. We assume we know those things. Those will be given on homework 6. Step 1 is compute D, which is 1 over A, 1 over B, 1 over C, 0, 0, 0, 0, 0, 0. And D inverse, which is even easier. It's just A, B, C, 0, 0, 0, 0, 0, 0. Next, let's see, we've got the horizon points. I should be clear that these are undistorted horizon points in the image plane. Step 2 is we compute for each point SI prime is D T C to P XI normalized. Okay. The next step is we form the matrix H. And H, I didn't name this during the derivation, but it's just this. It's what you get when you take all of the S primes and stack them. So SM prime transpose, right? And then 4 is solve HN is equal to a vector of 1s in the least square sense for n. And then step 5 is that the position is n transpose n minus 1 to the negative 1/2 power t from p to c d inverse n. All right, and then just to be very clear, this is the vector from the spacecraft to the planet in the camera frame. So you will need to put, a negative out front if you want the actual position of the spacecraft in camera frame. And that's it. That's everything that you need to do for homework 6. So for homework 6, you are given a image of Pluto that was taken by the New Horizons spacecraft. You'll need to do a little bit of digging, although I think I get you started on the right track to find the camera parameters. And you'll also need to do a little bit of manual image processing. You're welcome to write an algorithm to find horizon points, but it's perfectly fine for me if you just want to open it up in MATLAB or even Microsoft Paint and then just click on horizon points. I forget the exact number that I recommended. I think it was something like 8 to 10 horizon points, but that's in the homework handout. And that's it. And then you'll code up this algorithm. I mean, the whole thing should be lickety split, shouldn't take very long. And you've got your, first pass OpNav solution. Now, I should be clear that if you were going to code this up for a real spacecraft, there would be many additional steps of trying to add robustness and automation to your image processing. But the kind of engine, the reactor core that goes from horizon points to your spacecraft position estimation is what we've learned today. This is basically that. And so, yeah, that's my outline of horizon-based OpNav. Thank you for bearing with me for 25 plus minutes while my computer turned into a potato. I'm going to go ahead and dismiss everybody, but I'm not going anywhere. I'll stick around if you have any questions about this or about homework 5. Thanks, everyone.